Hello my people, welcome back. Don't forget to subscribe. So let's go into the video. So I'm gonna talk about how to create stable heavy elements. Guys, I've been making my theoretical research and I think it is 100% genuine, and there's no way you're going to prove this wrong. This is the original work. It works as the sun. This is like the process the sun goes through to actually start producing heavier elements. So as you see, stars die. Some stars which are super heavy, some of them when they produce elements that are so heavy that they can't that they have different properties that end up creating a black hole. So now let's and the star dies and it goes into supernovae whatsoever. But here are some of the 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 super heavy elements that we can create. Let me show you the process. Actually, this is the thing to prove you that these super heavy elements can exist. You know, the super heavy elements that we have now, they have a high proton to neutron ratio, which is exceeding the stability one, the stable ratio, which is 1.5 to 1. So when you start to use this experiment of mine, which I'm going to talk about, you are able to produce these elements under the ratio of 1.31, the stable version which you can manage. So you can produce up to 1.20. So I'll be showing you how to do it and the elements to use to start producing. So this is the experiment you need to follow, and please, you can add yours to maintain. I'm going to give you a heads up, but you can add how to use magnetism to maintain the plasma, whatever, and as long as we have to make the system at least 50% efficient. So let's go into the video. Wow, this is going to be amazing. You're going to be mind blown. So this is a take note. Remember, these unstable elements, they have higher numbers of neutrons, okay, which are creating a high proton to neutron ratio. As to be stable, the nuclear force in the nucleus of the atom has to be stable. When the number of neutrons is also moderate, doesn't exceed the attraction force, that is the nuclear force in the nucleus of the atom. So now this is the experiment to show that how you can synthesize a super heavy element. Yes. How, guys? Now let me hope you are happy. So now let's go into this. This is the only natural way to synthesize super heavy elements. So now this is my theoretical research, which is 100% genuine. Yes, for anyone who will throw out, you will 100% produce a super heavy element with this method. So now what you need is pressure, collisions, and heat. So now fuel is nuclear fission. You need a fuel source which generates heat. You need like unstable element, that, like, let's say a radioactive uranium isotope. You can use that one to create a more, and to reverse that energy to create a more stable isotope of uranium, which has fewer neutrons to protons, which creates a proton to neutron ratio, which is 1.3, which is under the stability, the stable island. So let's go. A nuclear fusion heat source is attached to the pressurized heat chamber made of thick materials. Heat is transferred from the nuclear fission reaction and fed into the pressurized chamber at full power. In order for the nuclear fission to occur, between different elements, in which there is a presence of a high combustion gas like helium to heat these elements to evaporating point for total nuclear fusion of the required element to form at the desired nuclear fusion temperature. Once the desired temperature at which the desired super heavy element is reached and maintained for complete nuclear fusion, temperature can be decreased by using liquid nitrogen because it's very cold, and the super heavy element is extracted. So now let's dive into how to produce stable uranium, because it's now the abundant unstable element we have, but there's also a stable element of uranium people don't know. There's stable element of uranium. We have everything here, but we just need to create that heat and pressure so to synthesize stable uranium. And we must put in a lot of energy to produce just a small output. But remember, producing this stable heavier elements can have a lot of properties which will be useful, maybe for curing cancer. We can use them in medicines, we can use them in a lot of things, in aging, in creating stem cells that last longer, you know, creating advanced technology. There is no need for computers to require chips, to require cooling systems, and these materials, they can handle all the heat and they can function under even extreme temperatures. Imagine having a phone that can function even under extreme temperatures, like extreme heat, extreme cold. That would make technology even more fast, even like they are fast in receiving, they can even detect small signals. So now let's go into this. Let me show you one of the elements that we can use to create stable uranium, guys. This is totally researched, I put in my work, and I have to take the credit. I'm the first one on this. No one should take credit on my work. So everyone will be, I know the secret. Also, this is called the delta fusion chamber that produces heavier elements. So let's go. You can add the coils in order to control, to help with the chamber was not to get melted because of high temperatures. But remember, it depends on the amount of the element you want to convert. It is the amount of heat you are going to use and the time duration, so that the entire elements, they can totally react and produce the results you need. Now, to produce stable uranium atom, it must have less neutrons to proton ratio, which is doesn't exceed the stable proton to neutron ratio. Okay, you know, when neutrons are exceeding the ratio, you know, there is instability and radioactive, they go under radioactive decay. So now nowadays you can use an element called dysprosium isotope, which has 66 protons and 90 neutrons. You have iron isotope, which has 26 protons and 30 neutrons. Now we have another pair is titanium, which has 22 protons and 26 neutrons. And the titanium goes with ytterbium, which has 70 protons and 100 neutrons. Lanthanum has 57 protons and 82 neutrons. And the bromine has 35 protons and 44 neutrons. Moly molybdenum has 42 protons and 56 neutrons. Tin isotope 116, no, tin isotope, let me call it tin isotope, which has atomic mass of 116, has 50 protons and 66 neutrons. So with these pairs you can create different isotopes of uranium which are stable and they don't go under a radioactive decay, which are under the actually, let me read this before I continue to another element which is you guys would love, which you would love to discover, and it might have even different properties which you can imagine. So now we have this is the note you should note before you start to complain and start arguing. For stable atoms, the maximum neutron to proton ratio is 1.5 to 1. Atoms with too many protons compared to neutrons, or vice versa, lie outside the bond of stability and will undergo radioactive decay to achieve a stable configuration. Okay, so now everything I have listed, those pairs, when you add their neutrons and divide it by the number of protons, you get the proton to neutron ratio. I swear to you, will never get, with those numbers which I have given you, you are not going to get a proton to neutron ratio which is above 1.5, or the neutron to proton ratio will be below 1.35, the stable island. And remember, these isotopes will have different properties. Now let me talk about this. The person who inspired me to start to make research and really know that how can we actually synthesize element 115 Moscovium, Bob Lazar. Although I don't know if his story is real or it is fake, but guys, I don't know to read his mind. But if he's lying, guys, Bob Lazar, you are lying. But if you're not lying, let's go into this, how to create Moscovium element 15, and let's check this out. To create stable element 115 Moscovium, which is called Moscovium, dysprosium. This pair, number one pair, is dysprosium, which has 66 protons and 90 neutrons. We have indium, which has 49 protons and 66 neutrons. We have barium and palladium, which has 59 protons and 82 neutrons. We have zirconium, which has 40 protons and 50 neutrons. We have ytterbium, which has 70 protons and 100 neutrons. So with having these elements under pressure, under the nuclear fusion process, which I've described the process there, and applying using any stable element like this nuclear which undergo radioactive, actually striking them with the neutrons produces a lot of heat, which that heat can be trapped in the system and burn this helium gas, which burns these elements, and they evaporate, which because they are dense, they won't leave the other chamber. They will keep reacting with each other until when the heavier element is formed, it sinks to the bottom because it's heavier than, and it can be extracted in any way. So the process can take according to the period of time and the heat applied to the system. Nitrogen can be used as a cooling agent to create pressure difference. So guys, this is the only way. Let's see the world change, but I think it require huge investments because it's from somewhere from $1 million to and above. So guys, this is called the delta. I call it you should give me the credit. You should call it the Delta Sam Collins UG fusion reactor that creates the super heavy elements. So thanks so much. So it would be much easier to create small grams of these super heavy elements than creating kgs. With creating kgs, it require large amounts of energy, but creating small like 10 grams, 50 grams of these heavier elements won't require a lot of energy and a lot of time. That means you can create them through your time. So guys, thanks so much for following through up to here. Don't forget to subscribe.